My name's Lynne Regan. I'm at Yale, and I would say I'm a practitioner of conversion research, and I'm also director of our interdisciplinary graduate program and the Raymond and Beverly Sackler Institute for Interdisciplinary Research. And in this session, we have Katerina Thompson, Simon Mockery, and Andrea Stiff, and we've organized this section to start with a discussion of educational and institutional structure to allow that. We then have a talk on the specifics of what it's really like in the trenches to teach physics to biologists, and then we move on, both of those at the undergraduate level, and then we move on to the last talk, which is, sort of brings together both those issues but at the graduate level. And so I'd like to ask Kachi to come and give the first talk.
Okay, thank you. So over the last decade or so, there have been a series of influential reports in undergraduate biological sciences. And among many recommendations, one of the recommendations was to make courses and curricula more interdisciplinary. Another emphasis was that we should be focusing on competencies rather than courses, the idea being that sticking within the disciplinary boundaries of traditional courses squashes innovation. It's possible to do many more innovative things in undergraduate curricula if we think about it a little bit more broadly in terms of what students need to be able to do and what we want them to learn. So if we think about our traditional undergraduate educational paradigm, it's built on units of courses. So boxes here representing courses. You have your course for biology, your course for physics, for example. In the biological sciences, students take other boxes in chemistry and calculus. And we expect them pretty much on their own to be able to make the connections between all of these different courses and come up with a cohesive whole and be able to draw from all these different disciplines in their future problem-solving situations. But more often than not, students fail to make a lot of these connections that we hope that they would make. So there are various alternatives to this, but one that's been highly successful for us at the University of Maryland is to design the courses so that the connections between the disciplines are made explicit. And it works best if this is reciprocal. So for example, our introductory biology classes draw in physical principles. Our physics for the life sciences makes explicit connections to biology. So this is sort of an overview of our undergraduate biology curriculum, some highlights of the curriculum. And for about the past 10 years, we've been working to strengthen interdisciplinary connections. So I'm going to mention a few of these initiatives in a little bit more detail, and my talk is really going to focus not so much on the content of these initiatives, but how we've worked together as faculty to bring about these changes to the curriculum. And it's been a little bit different in each of the different examples. So one of the examples I'm going to highlight is MathBench, which is a series of online modules that have been inserted into various fundamental biology courses and bring a little bit more of a stronger quantitative emphasis into those courses. We've also created an organismal biology course that's part of our intro sequence. The students take it in the first or second semester of their sophomore year, and it weaves in physics, math, and chemistry. Our chemistry sequence has an accelerated entry into organic chemistry, and that creates an opportunity in the fourth semester for a very biology-focused laboratory experience for the students. We have a calculus for the life sciences sequence, and you'll be hearing a lot more about our Nexus Physics course, which is a broad collaboration as part of a Heritage Medical Institute funded multi-institution project that is creating a new physics for the life sciences. And then, as on many campuses, there's an array of upper-level courses that are transdisciplinary in emphasis. So first, MathBench, there's 37 interactive online modules. The students complete them outside of class time usually, and they're keyed to specific content area in introductory biology, microbiology, genetics, and so on. This was designed by a small development team in consultation with individual faculty members. So faculty showed us places in the curriculum where there was a need to add quantitative emphasis, and the Math Bench team designed a model to plug into that part of the curriculum. The organismal biology course had a goal of understanding the fundamental mathematical, physical, chemical, evolutionary, and genomic principles that underlie the structure, function, and diversity of life. And this was designed by a team of biologists with expertise in different taxonomic groups, and it was team taught also by 2 faculty members. There was some consultation with a physicist kind of down the road after the course was developed, but it was mainly developed by biologists. And the faculty development team created a consensus syllabus. They broke into smaller subgroups and created PowerPoint presentations and fleshed out some of the topic areas, and then they shared all the course materials that they developed. So again, this wasn't a highly interdisciplinary group, even though the topic area, the emphasis of the course was fairly multidisciplinary. In the Calculus for the Life Sciences course, what we wanted to do was focus on the areas of mathematics, so calculus and also some probability that are most important for modern bioscience research. And the math faculty were very accommodating. They basically said, just tell us what you want us to teach and we'll do it. So we assembled a team of biologists. They reviewed a lot of existing texts for this purpose, selected one they liked, gave it to the mathematicians, and the mathematicians took it and ran with it. Another thing that was done in the creation of this course that was a little bit unusual, certainly unusual for our campus, is we added a second recitation section. So these courses typically meet in large lecture halls 2 or 3 times a week, and then they have one problem-solving session a week. That's the sort of traditional model. We added a second problem-solving session per week, and instead of just having one teaching assistant who was a mathematician, we had a second teaching assistant that was a biologist. So it was not team taught at the faculty level, but team taught at the graduate teaching assistant level, and the biology teaching assistants took a lead role in developing the problem sets that the students did during those recitation sections. So the students were actually seeing biology in practice. Many of the context for those problems came right out of the graduate students' research. Now I'm going to focus on the Nexus project, and as I mentioned previously, this is a collaboration between 4 campuses that are all addressing the needs of the modern pre-medical curriculum. So what does it take to get a student ready to go to medical school? What kinds of competencies and knowledge do they need to bring into that situation? And we found there's a lot of overlap between what a pre-medical student needs to be a good doctor and what a biologist needs to become a good biological researcher. So most of the changes that we've talked about making during the course of this collaboration cut across the biological sciences curriculum. This collaboration has been funded by the Heritage Medical Institute. It's called the Nexus Project, and the particular part of the project that Maryland has taken the lead on is developing a Physics for the Life Sciences course. So we're focusing on the physics that's most important to modern biology, which means that the content of the course has been revised to downplay some of the things that students were finding in their traditional introductory physics course and put more emphasis on other aspects of the curriculum. It uses examples that have authentic value to both biology and physics. So they're not trivial examples from biology. There's no spherical cow. There's a vetting process that all homework assignments and examples and group work go through that gets input from both biologists and physicists to make sure that it measures up from both disciplines. One of the more radical things we've done is we don't assume that students, when they walk in, have no knowledge of any other science. Most biologists, when they take this course, are in their junior year. Sometimes they put it off to senior year. Historically, they have, because they haven't seen its relevance to other biology coursework that they want to take in the upper level. We're trying to incorporate it starting towards the end of the sophomore year so that students can use the physics in advanced courses. So we assume what students actually have when they walk in the door, which is a year of calculus, at least a year of biology, and some general chemistry under their belt. And that's more than just a prerequisite. The students are asked many times during the course of the semester in both the lecture and the laboratory to make connections between what they're learning in physics and what they're learning in other courses. They're asked to bring in their knowledge from the other courses into the physics classroom, and they're asked to reflect back on how the physics they're learning helps them understand the biology. So we got to this point. We're now in the third year of implementing this course, and we've scaled up to 2 lecture sections serving 400 students each semester. This clip art was not what I picked. It's actually the clip art that our lead physicist, who taught the pilot versions of the course, uses to explain the process when he gives talks about this course. And it didn't come easy. I think we were somewhat naive going into the process based on our experiences in other courses that had been developed in the curriculum. But there was intensive content negotiation. The first round, we tried to duplicate what we did with the mathematicians, and the biologists met as a group. There was about a dozen of them that came up with an ideal curriculum, what they thought was important for biology students to know, and we presented that to several physicists, and they said that won't work. And that wasn't just coming from tradition, that was coming from over 20 years of pedagogical and epistemological research into how students learn physics. So we couldn't start where the biologists wanted to start, and we had to take into account what was already known about what students struggle with and what they need to be able to advance in their learning of physics. In round 2, we tried to bring everybody together, all the stakeholders, everyone who cared about the teaching of physics and the learning of biology students, and we tried to talk it out and see where everybody was coming from. So it was a very large group. And we started with what topics to include and exclude. And it quickly turned fairly contentious. There were a lot of strong opinions in the room, deeply held beliefs, which was actually not a bad thing. It's good that, I love that our faculty are so invested in our students' learning and have such strong feelings about how we should be teaching. But there were a small minority of faculty who dominated the conversation, and we didn't reach consensus. A lot of voices weren't heard. We tried this for a few meetings, and we weren't making much progress, and a lot of people who had been engaged at the beginning started not showing up to the meeting, so we took a step back. So that was also not a successful approach. But we took a step back and we regrouped, and we created a smaller working group. We had 2 physicists, 2 biologists on that small working group. We had expertise in science education. We had expertise in biophysics. So it was a nice, well-rounded group to start with. And there was also an administrator involved to kind of keep everybody marching in the same direction. And then that group started to put together a curriculum, and they pulled in additional input from faculty in several different ways. So they solicited white papers from biology faculty who taught at the upper level to find out what expectations they had for students coming out of introductory physics. There were also very focused discussions on particular topics where biologists, physicists, chemists, and mathematicians were invited to join in and provide input. So some of these conversations focused on thermodynamics, for example. So those cross-cutting topics that students are likely to encounter in multiple courses. And they made all content open for comment using a wiki form, so anybody could go in, see what was being written, see what was being planned for the students. And so our assessment data indicate that the students are learning physics as well or better than they did previously, and they also have a greater appreciation for quantitative methods and physical principles for understanding biological phenomena. So I'm just going to leave you with one other success. There we go. One other thing, food for thought, there are a lot of models that are used for creating interdisciplinary curricula, and perhaps the simplest one is one faculty member with an interdisciplinary background creating a course that's highly transdisciplinary. That doesn't require a lot of negotiation, but it's at risk of not being sustainable because if that faculty member moves on, leaves the institution, changes teaching responsibilities, the course might go away. In the middle, we have a team teaching model, different disciplinary expertise working together to create a course. But this is also somewhat vulnerable because if either one of those faculty members moves on, the course might not continue. And then finally, the approach that seemed most productive for us is a group approach, a collaborative approach. It can be somewhat tricky when there are a lot of stakeholders, and it can also be tricky when the faculty charged with teaching the course are a different set of faculty from the ones who are receiving the students in later parts of the curriculum. But this has greater potential for sustainability because there's shared interest, shared investment, and shared responsibility. Thank you.